Okay, so hi, I think I've met most people, but in case I haven't, I'm Keaton. I'm a postdoc here at the CCA. And since Rich couldn't give his talks this afternoon, I just threw together a quick presentation, probably only an hour or so, on spectral methods for solving PDEs, which is what I work on. So we've heard a lot about other methods for solving hydro and MHD equations, mostly finite element or finite volume, finite difference methods. But spectral methods are a very different type of numerical method with very different properties, and they're not suited to every problem, but they're really good for some types of problems. So I think they're just good for everyone to know a little bit about. So one quick motivation is it's I think still the case that the largest turbulence simulations in the world are ran using spectral methods. So these are uh, very large scale incompressible turbulence simulations on the order of 8,000 cubed Fourier modes. So these are the sort of the highest Reynolds number domain filling turbulence simulations in the world. And spectral methods are very expensive methods. So you'd say, why would you choose that method if you're trying to do the world's biggest turbulence simulations? But the trade-off is that they're extremely accurate. So you get a lot of bang for your buck using spectral methods. So to actually resolve things at these really high Reynolds numbers, it's the scaling works out such that the accuracy over the cost still improves with large scale. If you're interested in the types of flows that spectral methods can handle, and I'll get into the limitations of those later. So just like the four quick sections, first I'm just going to do a general introduction to spectral methods. Then I'm going to tell you a little bit about this code called Daedalus, which is a spectral code that I developed during my PhD. Then I'll show some applications and examples, some fun movies and stuff. And then if we have time, we can talk about spectral methods for curvilinear domains. So if you want to use spectral methods in spheres or disks or things like that, there are some special things that you have to do. Okay, so first of all, yeah, what is a spectral method? So spectral method is probably one of the easiest numerical methods to describe and also pretty much the most general. So a lot of the other methods we've heard, we heard about specific implementations that preserve specific properties of the equations or the solutions and sort of efforts and the history of tailoring these different methods to maintain certain conservation laws and things like that. Spectral methods don't do any of that. They're a very simple procedure. You say, instead of expanding my unknown variables, which here we're just going to call u, over some set of grids or faces or edges or volumes, we just write it as a sum of coefficients times a set of global basis functions. So that's our representation. That's our discretization, is that this would be an exact representation if we kept an infinite number of terms in this series expansion, but instead we're going to truncate the sum at some fixed n, and that is the sense in which the variables are discretized. And then say we have a partial differential equation, which I'll just write in general as h times u equals f. So h is here we'll consider it to be a linear differential operator. F is some function that could be a nonlinear function of u. That's just anything else that we put on the right-hand side. And the way that you solve the equations with the spectral method is by projecting the equation. So you insert the expansion into the equation, and then you project the resulting system against another set of basis functions. So in the traditional parlance of the finite element community, and then also in the spectral community, we call these trial functions for the functions phi that we're using to expand the basis, or to expand the unknowns, and the test functions are psi, these ones that we're projecting against. So this is how you discretize the equations. You do this projection for some fixed number of test functions, and then you end up with this matrix system here. This looks just like quantum mechanics, because that's how quantum mechanics works. So you just have this discrete matrix system times the vector of unknown coefficients equals the vector of the coefficients that come from projecting the right-hand side against the same vectors. So at this point, this general PDE is just reduced to a matrix problem. And this is how all spectral methods work for pretty much all equations. So they're very generalizable and easy to adapt to different PDEs. So we can do systems where we just have multiple variables and multiple equations. And you just follow the same exact procedure and you just get a larger matrix system that you're solving. The fundamental limitation of spectral methods is that this only works in simple geometries, right? So we have basis functions that do a good job of representing functions on periodic intervals. Those are Fourier series. You can use polynomials for closed intervals. I'll get into some of the details of that. You can use spherical harmonics for spheres, things like that. But in general, you're not going to be able to discretize around complex geometries. So this really works well only for boxes, cubes, spheres, those types of simple domains. The other big advantage, which I alluded to earlier, is that they're very accurate methods. So if you use the right set of basis functions, then you'll typically get exponential convergence to smooth solutions. So if your PDE has a smooth solution, as you add more modes, as you increase n, then you're going to converge exponentially towards that solution. So this is really the power, right? As opposed to a second order, third order, fourth order finite volume method. This is basically like an infinite algebraic order or exponential converging algorithm. One of the other big downsides, depending on what you do, is that these methods give you essentially equivalent resolution at all points in the domain, so they're not really adaptive. So they don't lend themselves very well if you only have small scale structures in a small volume fraction of your domain. Neither good nor bad, I would say, is that another limitation of spectral methods, though, or requirement of spectral methods, I would say, is that they require that the PDE solution itself is resolvable. So it turns out that this method has very little and essentially no numerical dissipation at the grid scale. So you can't rely on Isles simulations like we heard about before to actually dissipate turbulence, for instance. If you have a turbulent hydrodynamic system, you have to explicitly include viscosity or magnetic diffusivities, things like that, so that the PDE you're solving actually has a smooth solution at the scale at which you're resolving it with these spectral coefficients. So to a lot of people, this is a drawback if they're used to working with these implicit LES schemes and other numerical methods, because they're saying, they say, okay, well, I can't do as high Reynolds number flows in the spectral method, for instance, because I can't just have my solution go all the way to the grid scale. I have to like roll it off by adding an explicit dissipation. But I think the other side of that is you could argue that you're sort of controlling what's happening at the grid scale a lot better this way, right? You're forced to actually add physical terms that regularize the solution at the scale that you're resolving it. And so you know exactly what those terms do on the small scale, right? So if you're dealing with a process where you're not sure, like maybe an MHD turbulence, what is happening at the small scale and how that feeds back up to large scales, then it's hard to be confident maybe that your numerical dissipation from your numerical scheme is actually representing the right sort of like subgrid physics. Whereas here, you're forced to specify that yourself. Okay, so just a few details on the most common spectral series here. So the most common one for sure is the Fourier series. So Fourier series converge exponentially for functions that are smooth on periodic domains. So Fourier series are used to simulate periodic boxes, very, very commonly. So they have a few important features, though, besides just this exponential convergence. One is that you can compute the coefficients from the values on a grid in order n log n time using an FFT. So this is a fast transform. So for instance, if you need to set up initial conditions on the grid and then compute the coefficients, or if you need to compute nonlinear products, that's typically done in grid space. You can switch back and forth between the modal representation and the nodal representation of your solution very quickly. The other really nice thing about Fourier series is that the discrete form of the derivative matrix of the derivative operator, so the derivative matrix, is diagonal, right? So that makes solving PDEs with Fourier series very simple, because typically the PDE is completely separable, and you can just solve a separate ODE for each of the Fourier components. And the only coupling is in the right-hand side, not in the linear terms. If you don't have a periodic dimension, though, then the basis of choice is the Chebyshev polynomial family. So these are a series of classical orthogonal polynomials. They're orthogonal on the unit interval under some weight. They can be defined trigonometrically with the change of variables relating z to the cosine series. And the interpretation is that basically if you draw cosine functions on a cylinder and project them into the plane, then the projections of those cosine functions are the Chebyshev polynomials. So from the simple change of variables, you inherit a lot of the nice features of Fourier series. So if you're trying to solve a problem just in a closed domain, and you use Chebyshev polynomials, you'll get exponential convergence to solutions. You get a fast transform, because you can use the DCT to convert between the polynomial coefficients and the values on a grid. But the big drawback, the big difference between polynomial spectral methods and Fourier spectral methods is that the derivative matrices are no longer diagonal. And in fact, for regular Chebyshev polynomials, they're dense. So that looks like this. If I take the derivative of a Chebyshev polynomial and I project it against another Chebyshev polynomial, I get a dense upper triangular matrix here. So this would make solving PDEs using these very difficult, and solving, back solving this matrix is slow, or computing a factorization in inverse is also slow order n cubed. So for a long time, this sort of limited how far people thought you could push Chebyshev methods. But it turns out that if you actually take advantage of using different trial and test functions, those functions that I introduced at the beginning, you can get much better behaving matrices. So in particular, there's a different type of polynomial that is sparse in the derivatives of these Chebyshev polynomials. So if we sort of project our equations against a different set of functions than we used for the variables, there's actually a procedure you can do and basically make any system of equations represented by banded matrices. So these are no longer diagonal, but they're still fast to solve compared to dense matrices. So the procedure, if you have a PDE, is kind of like this. So you take a PDE here. This is just a linear wave equation. We can reduce it into a system that's first order in both time and space derivatives. That gives us this system of 3 equations. And then that system I can just write in this block form. So this block operator form acting on my set of unknown variables. And the spectral method really just looks at this whole system, and it goes through one by one, replaces these block operators with the banded matrix forms that we get from the previous slide. And at the end of the day, you just have a large coupled system of ODEs where the linear portion is represented by a banded matrix, and then you could have, again, general nonlinear terms on the right-hand side. And this is the full spectral method. So at this point, we have ODEs, and we can discretize in time with any method we want. So I haven't said anything about time stepping. That's because the whole business of the spatial discretization completely decouples from the time discretization of spectral methods, which is a really nice advantage. So you can use basically arbitrary high-order time steppers here. You're not limited to a certain type of time stepper just based on your spatial discretization. Okay, so the code that I worked on during my PhD for solving general PDEs with spectral methods is called Daedalus. We have a website. So this is the development team. So I guess going from left to right here, this is Daniel Akane, who's a postdoc at Princeton, and he's going to be faculty at Northwestern in a year or so. Jeff Oishi is now faculty at Bates College up in Maine. Jeff Vassell is a mathematician from University of Sydney. And then Ben Brown here is in astrophysics at CU Boulder. So the point of the code, I guess, is to just provide a nice package for doing that exact procedure I just explained to discretize general PDEs using these sparse spectral discretizations. So the code actually has no built-in equations. You sort of symbolically enter your PDEs, and it parses them into this system of sparse matrices. It can handle initial value problems, boundary value problems, and eigenvalue problems all in the same framework. We get high accuracy solutions because we're using global spectral methods again, but it still is a pretty speed competitive code overall. So the parsing procedure that we use produces nearly optimally sparse matrices for general systems of equations. And then when we're actually integrating those equations, at that point, you're just doing time stepping, FFTs, and sparse matrix solves. So all of those things we can use compiled libraries for. So we use FFTW is a really good FFT library. Superlu and other numerical linear algebra packages give you fast compiled routines for doing these matrix factorizations and matrix solutions.
So does the user specify the test functions, or does the code optimize that somehow?
So yeah, so the user specifies the trial functions essentially, right? So if we go back here. So when you describe your domain, that basically defines the trial functions. And then what the code does is the code picks the test functions. So the code looks at your equations. As it parses the equations, it determines which test functions to use to give you an optimally banded system. Yeah. Okay, yeah, so it's all, calls compiled libraries. The code's written in Python, so there's an easy to use high-level interface, and it's automatically MPI parallelized. So again, the big restrictions, right? Simple geometries are restricted to spectral geometries. Yep. So I think I have a slide on that a little bit later, but quickly, so the code detects the separable dimensions of the linear portion of your PDEs, and then those matrix solves are trivially parallelizable because they're separate, right? They're block separable. And then I guess the other restriction, right, is that there's sort of no subgrid dissipation, so you have to enter a fully resolvable PDE with a regularized solution. So this example before, really what Daedalus is doing is it's, you type in your equations like this, it produces this system, and then the system takes the form of this general matrix system, which is the thing that the code actually knows how to solve. So it just says, no matter what PD you give me, it just looks like this, so I'm just gonna use the same procedure to solve this. So the actual code so a script to solve the wave equation basically looks just like on the previous slide. So here you create a domain that consists of a 64 mode Chebyshev series. You create an initial value problem with these variables, and then you just type in your equations in first order form along with boundary conditions. And that's how you specify the PDE. Again, the same system handles IVPs, eigenvalue problems, and boundary value problems. So I'll say a little bit about the right-hand side. So I said before, I kind of just said, okay, we put everything nonlinear into the right-hand side. But it turns out that's where most of the computational cost of these methods lies, right? So we're time stepping by repeatedly solving this sparse left-hand side matrix against a right-hand side vector that comes from computing the right-hand side at a given time step. And what goes into that is basically all of the expensive part of the algorithm. So to compute nonlinear terms, which are on the right-hand side, you have to transform your variables to the grid. And that involves both doing FFTs, but also parallel communication, because if I distribute the coefficients over different processors, then to do the FFTs over the distributed directions, I have to send the coefficients back and forth before, so I can do FFTs local to each process. So a given right-hand side call involves MPI all-to-all communications, so this is a pretty heavy communication step compared to other types of methods, as well as these FFTs. Okay, yeah, that's all I wanted to say there. So the parallelization, so if you have a multi-dimensional problem, then say U, depending on X and Y, is just expanded in the direct product of a series in X and Y. And if, say, the X direction here, these are Fourier modes, then the linear portion of these equations, because derivatives don't couple different Fourier modes, is separable. And you basically just get a bunch of one-dimensional problems, say, in Y, that I can solve independently on different processes. Yeah.
So this is about the nonlinear terms.
Yeah.
So this is something I never understood about spectral methods. So I know everyone, to treat the nonlinear terms, they basically go back to a grid,
Yeah.
like evaluate the nonlinear term, and then go back to spectral.
Mm-hmm.
But I know in some cases you can probably like take the nonlinear term, basically do the projection like analytically. Like you can calculate coupling coefficients analytically in a lot of cases.
Yeah.
So I don't know why people prefer to do this whole thing on the grid rather than do it analytically. It's faster.
Yeah, that's right. So if we say, just consider like the nonlinearity in Navier-Stokes, so just like one component, scalar component of it, right? So we end up with something like a quadratic nonlinearity, multiplication between two terms, right? So if U is the sum over n of un phi n, right? Then you're right, I can compute a term that looks like phi, we'll go with k, uu, right? That's the term that actually ends up in one row of the discrete right-hand side. Okay, and if we just expand that out, so over, right, get that. Okay, is that big enough to read? Okay, so you end up with, right, a sum over phi ij times coefficient I, coefficient j, and then this is the coupling coefficient you said, right? You can pre-compute this for a general term. But still computing this, right, these values are changing every time step, right? So computing this is still an n squared operation, right? Because this is a sum over I, this double sum over I and j, right? This process, this is like an order n squared evaluation, right? Doing this like matrix method. Whereas if I take the FFT, that's an n log n, right? That's 2 n log n's, right? I have to do an n log n for each variable. In this case, it's the same. Multiplication on the grid is order n because it's pointwise on the grid, right? And then n log n coming back. So asymptotically, I'm trading n squared operations for multiple n log n operations. So this is called the pseudospectral method. This is why we evaluate all the nonlinear terms on the grid. Yeah, a fully spectral method is one that would just do that n squared computation and never go to grid space. Always just live in coefficient space. That's right. Yeah, yeah. But usually you have at least one, periodic dimension, right? If you're doing spherical harmonics, for instance, right? Then yeah, exactly. The latitude discretization is not periodic, but the azimuthal one still is. Yeah. Okay, so parallelization, yeah, you just get separable problems. Okay, so for a multidimensional problem like Navier-Stokes and Daedalus, you just type in the equations component-wise. So again, like Daedalus doesn't implement Navier-Stokes. Most people are using it to do hydro simulations, but the way that you enter Navier-Stokes is just like this, right? You specify variables. Again, it's reduced to first order in z derivatives for technical reasons, but it's not too important. So this is incompressible Navier-Stokes, so you can see you just directly impose the incompressibility condition, the two momentum equations. So we have dtu, linear terms on the left-hand side, remember, so this is the viscous term, so this is minus r times the Laplacian of u, pressure gradient, and then the advective terms on the right-hand side, and then the boundary conditions down here. Yeah, that's right. So if I take two Chebyshev derivatives, then I don't end up in that right polynomial basis where I have banded matrices. So instead, we reduce the equations to first order form in the Chebyshev derivatives, right? So I've introduced these extra variables, uz and wz, and defined them with these constraint equations, right? And now I have a system of equations that's first order in z derivatives. Okay, so some just example movies. So one really nice thing about spectral methods is that since you are basically integrating the coefficients, you directly have access to the truncation error of your simulation. So here's a plot of the KdV equation. So this is Berger's equation with a regularized with a dispersive term. So here's the initial condition in space. So this is a wave that's going to fold over and create a shock, classic Berger solution. But here I'm plotting on the bottom as the movie goes. We're going to plot the amplitude of the coefficients of the solution as a function of wave number. And so we can see directly that like this initial condition, for instance, it looks pretty sharp here. I might worry that I don't have enough modes to represent this, but we can see that our solution coefficients are falling to machine precision well within the number of resolved modes. So this is just a 1D problem, but this point like holds with the multidimensional simulations too, right? Just by looking at the amplitudes in coefficient space and looking at what the amplitudes are of the last retained coefficients in your expansion, you know directly what the truncation error of your simulation is. So you basically know, okay, I'm only integrating this to 10 to the minus 6 accuracy, or maybe all the way down to machine precision. This is also sort of a fun problem because although it's pretty simple, it sort of illustrates the point about having certain subgrid physics. So if you do that same problem, so this is the Berger's equation integrated with 3 different types of regularization terms. So just a viscous term here, like a second derivative, a dispersive term, which gives you KdV equation, and then a Hilbert transform, which gives you an equation called the Benjamin-Ono equation. You can see that although the large-scale dynamics is the same, you start out with this triangle that forms a shock. The process that's actually causing the regularization of the PD at the small scale makes a big difference to the global solution, right? So all of these terms are nominally small. Oh, these regularization terms, right? So small viscosity, small eta, and small alpha in these models. But if you left them off and just wanted your numerical dissipation to take care of the subgrid effects, you would obviously get the same solution in each case because the rest of the physics is the same. So yeah, this is just sort of emphasizing this point that maybe the details of the subgrid physics are important, and so it's better to try to have an explicit regularization than just let the numerical scheme take care of that for you. There are soliton solutions to the KdV equation. This initial condition is not like a, yeah. Okay. So this isn't really a specialty of Daedalus, but I just thought I'd mention it. So you can also use spectral methods to form what are called spectral element methods. So these are sort of a hybrid of finite element methods and spectral methods, where you use high order polynomial representations within a given cell of a cell discretized simulation. So we heard a little bit before about like a linear versus parabolic reconstruction for representing the like internal state of a cell in a finite volume framework. But if you sort of take the limit of saying I'm going to use higher and higher polynomials to represent what's going on within a cell, you get a spectral element method. So here's just a fun 1D example where we've connected a bunch of 1D segments in a graph, and we're solving the nonlinear Schrodinger equation on them, and they're all coupled together. So each individual segment here has a maybe, I don't know, 30-degree polynomial representation within that segment, and then you can couple them all together through their boundary conditions and make this graph. So this is like a model equation, for instance, for pulses in optical fiber networks. The nonlinear Schrodinger equation is like a amplitude equation for optical pulses. This can be done for hydro too. We don't do this a lot, but it's used particularly in aerospace. You'll see discontinuous Galerkin methods and finite element methods, which sort of take this approach to do hydrodynamics. I want to say another word on the formulation of incompressible hydro in these spectral methods. So I had the code before for 2D incompressible hydro. Here are the equations just in matrix form. And so one thing to maybe point out is the way that we're handling the incompressibility condition. So that's the last row here, right? So along with the momentum equations, we are directly just imposing that div u is equal to 0. So this is also a bit unusual. A lot of other schemes basically use splitting methods to enforce constraints like div u is 0. So they'll basically take the divergence of the momentum equation, and then that'll produce a Poisson equation for the pressure. They will solve that equation to get a pressure, and then put that into the momentum equation and maybe do some correction later on. So this method, it fundamentally limits the temporal accuracy of your solution, though, because any splitting method introduces a splitting error that's something like second order in time, for instance. So it limits the order of the time integrators that you can use. But since these methods produce sparse matrices, it's actually efficient to just solve the whole coupled system directly. You can impose constraints directly alongside your prognostic variables. And without splitting, the implicit method is automatically enforcing those linear constraints, essentially using the pressure as a Lagrange multiplier here. So this lets you basically solve systems like incompressible hydro or other constrained differential algebraic equations with arbitrary order time integrators. So just a quick example of that. So this is those equations. This is Boussinesq hydrodynamics. So what the movie is the view from above of a fluid layer that's between hot and cold plates. So this is the classical Rayleigh-Bénard convection setup. And there's this regime sort of at low Rayleigh number where the instability forms these long rolls, and then those rolls wrap around and form these spiral patterns. So this is actually something you can see like on your stove at home if you put a little oil in it and you are very precise at how much you heat the stove and these types of things, then you can actually see this kind of pattern formation going on. But again, the point is, it's a fully nonlinear simulation, but we can do it with high order time steppers. So that case was ran with a third order time stepper, and you can show that you get this high order convergence and are not limited to the traditional splitting order of incompressible schemes. For compressible hydrodynamics, a common formulation is to include the hydrostatic background and evolve perturbations to that background. So here, this is a formulation of compressible hydro in pressure and specific density, or specific volume, sorry. So alpha is 1 over the density. And then we actually solve equations for the perturbation variables p prime and alpha prime. So that introduces, in the linear dynamics, we have the background terms, right? So the alpha naught and p naught are describing a hydrostatic background of an atmosphere or the radial profile of a star, something like that. And we basically, we're not solving linearized equations for the perturbation, right? We're solving the full nonlinear equations, but we've separated the variables into the perturbations and the background structure. And what this gives you is the ability to implicitly time step the sound waves around the background structure, right? Because all the terms involving the background structure and the linear variables are on the left-hand side, and those are integrated implicitly. So this is important because this lets you do fully compressible hydrodynamics, but without a CFL restriction from the sound speed. So that makes these methods really powerful for doing low Mach number flows, like of stellar interiors or planetary interiors. Because in those cases, right, the sound speed is very fast compared to the dynamics that we're interested in. So if we had to actually time evolve following the sound speed, we'd have to take extremely short time steps, and it'd be very, very expensive. So low Mach number flows are actually a very difficult regime for many like traditional compressible solvers. But here we can integrate implicitly over that sound speed and just have a time step that's restricted by the CFL of the advective nonlinearities, which are the terms that we're actually dynamically interested in. So here's a simulation of the radiative convective boundary in a star. So as a function of height, we have a radiative region here, and then that transitions to a convective region in the upper half of the domain. So this is done not in an inelastic approximation or anything like that. We can do the fully compressible equations, but then time step it on these dynamical timescales. And I guess this is an interesting simulation. We're looking at how the convective plumes come down and hit the tachocline and then excite internal waves that then travel to the interior. Okay, so I think one of my last examples in this section is a simulation of the compressible Kelvin-Helmholtz instability and a comparison with the finite volume code Athena. So so you sort of have this trade-off, right, between, so I said these spectral methods, they're very accurate, but they're also expensive. Like per mode, they're much more expensive than a finite volume method. So it remains to be seen for individual problems, like where does that accuracy performance trade-off actually leave you, right? Are you better off just doing higher resolution simulations with the low order method, or should you use a high order method? So that's a problem-dependent question, and so this was a paper that we did just looking at that for the case of sort of a moderate Mach number Kelvin-Helmholtz instability to see how the two codes, Athena, which is a finite volume Godunov code, and Daedalus compared. So here's a simulation. So we just have, two fluids of two different densities in an imposed shear moving past each other, and that interface rolls up into these billows. Sort of a classic, turbulence test problem. So this was ran at a nominal resolution and using Athena, and then we ran the same simulation at higher and lower resolutions. And so the simulation I showed you in the last movie is in the middle here, and then we have a higher and a lower resolution. So the question is to guess which simulation is high resolution and which simulation is low resolution. So who thinks this is the high resolution simulation? Who thinks this is the high resolution simulation? Okay, good. Lots of people fell for the trap. Okay, so the answer is that, yeah, of course, that was a trap. So that's not the case. It turns out that the simulation here is actually the higher resolution simulation with Athena. So that's weird, right? Because you look at these and you say, wait a minute, but this one is like clearly more turbulent, right? So shouldn't that be the higher resolution one? And it turns out that no, that this instability, this turbulence that's on the interior of this roll, is triggered by a spurious numerical instability. That's not a part of the true solution. So the true solution is that this roll sort of like forms and keeps winding up for a long time before it breaks into these small-scale vortices. And basically, the discretization error of the low-resolution finite volume simulation is triggering that secondary spurious instability earlier and earlier in time at lower resolutions, right? So as you add more and more resolution, you're actually doing a better job resolving the true solution, not introducing these numerical errors, and then are staying closer to the true sort of like laminar solution here. So if we put side by side for the same parameters, Athena and Daedalus, you can see that even at 4096 squared in the finite volume method, you still sort of have some early signal of this spurious instability developing in the core of the vortex, whereas with the spectral method, it's actually not there by 2000, and the 2000 squared to 4000 squared simulations are essentially identical. So the spectral method is pretty much fully converged by 2000 squared resolution. The finite volume one is not converged yet at 4000. So the question is, how far do we have to go with the finite volume simulation to get the same answer? So here's a plot of, this is the L2 error of the total density solution relative to the highest resolution spectral simulation. Okay, so that's the relative to the 4000 squared Daedalus simulation. This is a plot of the divergence, basically, of the lower resolution simulation in time. So it is still a chaotic problem. So you don't get the exact same solution. So the 2000 squared Daedalus simulation does diverge after a few turnover times, and the rate here is the Lyapunov exponent of the flow. So this is the actual rate at which you would expect, close by trajectories to diverge from a given reference solution. If we plot the Athena errors on top of that, we see that, the error is higher, but the most notable thing is that it's actually diverging at a completely different growth rate, right? So this is actually one of the indications that this instability that it's latching onto is spurious, and it's not, it's not just starting further away from the true solution and diverging at the Lyapunov exponent. It actually is getting the wrong growth rate. So as we add resolution with Athena, the amplitude of that perturbation goes down because we're getting a better initial condition, but still it's triggering this spurious instability at 2000 and at 4000, as we saw before, and even at 8000, it still is doing it. So at this point, we almost gave up on this project because we didn't really know what to make of it. But then someone at Berkeley had a computing allocation that was about to expire, and they had a ridiculous amount of time left. So we said, okay, well, we'll just burn all the computer time and run a 16,000 squared Athena simulation. And that one finally did it. So at 16,000 squared in Athena, you can see that you lie right back on to the right growth rate for divergences from the underlying flow.
How long did that take?
Ooh, I don't remember off the top of my head. I think that's a few million CPU hours. I don't think it's not crazy, but it was more than we wanted to spend on like one line in our test problem. So I guess I'll just mention, so again, like the fact that these line up is sort of coincidence. The point is that it is really the slope here, right? That you know that it's diverging with an unphysical instability because of this different slope. So if we plot the Daedalus 3000 simulation, for instance, that has the same slope, the Lyapunov exponent, but is seated at lower amplitude. So that's the takeaways. Essentially, right, it takes, for this particular problem, right, and I don't want to like generalize because this is this particular like moderate Mach number flow, so we expect a priori that this is something the spectral method would be good at because it doesn't have shocks, right, it has smooth solutions. But for this flow, right, for this low Mach number flow, you need, right, 8 times as much resolution with the finite volume method in each dimension to match the spectral method. So Athena, in terms of its speed per cell, it's about 10 times faster than Daedalus at equivalent resolutions. But if you have to use, 8 squared as many zones in Athena to get the same accuracy, now the Daedalus simulation is, 6 times faster or something than the finite volume simulation there. So the accuracy, so you hear a lot of times that people will quote, they'll just quote their zone cycles per second or something, right? They'll just give you a performance measurement with respect to time to integrate one degree of freedom, but comparing different numerical methods, the degrees of freedom mean different things. So that's not always necessarily an informative number.
Keaton, so that one started with
So that's a good question. So what you can show is that the evolution from this point, like roughly from this point onwards, is physical. So what we can do is we can run an Athena simulation, stop it here, right? Take that state, put it in Daedalus, and continue to integrate it using the spectral method, and then it follows that same line, right? So it's not that the integration is wrong. We think it's really an issue with the accuracy of the initial conditions and like error introduced early in the simulation by the discretization. So yeah, so it's possible that if you put on large enough noise, like noise that's matching the level of discretization error of the finite volume method, that would kick that initial condition into this other attractor, which is going off to that state. Okay, so I didn't have time to grab the video for this one, but here's a video of a, let's see, Orzog-Tang vortex test. So this is an MHD test problem. Let's see, this full screen work here. So this is a doubly periodic MHD vortex, and at moderate Mach number again. So the solution, okay, that's a fast video. So the solution here forms shocks. You can see the shocks running through the domain. But again, it's actually high enough resolution and includes viscous regularization. So even though the solution forms shocks, they're resolvable in the spectral method. So if we take a slice through that domain at some time, you can see the sort of shock fronts here and here. But then if you zoom in on one of these shock fronts and actually look at how many grid points basically we have across that shock, you can see that we actually resolve it because we're including enough viscosity to regularize the shock. And so even though it looks sharp by eye, you can resolve it. So spectral methods in this sense can do high Mach number flows, but this becomes obviously extremely expensive in 3D. You know, you can do it in 2D pretty well, but if you wanted to do this in 3D, those are pretty huge computations. Okay, so that was pretty quick. So I'll say a few things on curvilinear domains, I guess, but before that, any other questions on those examples?
If you're doing MHD, then does everything you said about controlling incompressible flows hold with the sort of div B equals 0 condition?
Yeah, so you have two options for that. You can use like a vector potential formulation, for instance, right? Or yeah, you can directly impose div B is 0 as a constraint equation alongside the induction equation, right? Just like we do with incompressibility. So yeah, compared to the other methods we heard about, right? So this is going to give you a solution that is not exactly divergence free. It does not exactly satisfy div B of 0, right? Because we're not making an exactly conservative scheme. But your solution will satisfy div B of 0 at the level of the truncation error. So the point of the spectral method is, okay, well, if you just put in viscosities, put in diffusivities, right? Then once you resolve the diffusive scale, you'll converge extremely rapidly, right? Exponentially quickly to the true solution. So that truncation error should be close to machine precision. So then effectively your integration will maintain div B of 0 to within machine precision over the course of the simulation. Yeah, I don't know. I think there's also, well, I don't know, maybe this is speculative, but I think there's a few ways to view conservation laws, right? So we know that we're trying to solve a PDE, and we know that the solution should satisfy certain conservation laws. So yeah, you might think it makes sense to like make a numerical method that directly imposes those conservation laws. But on the other hand, you can use those conservation laws to assess the general accuracy of your solution, right? So I can have an exactly conservative scheme, but run it in a regime where it's not accurate at all, right? So I shouldn't trust the solution, even though it, perfectly conserves angular momentum and energy, for instance, right? Whereas if you use a non-conservative scheme, you can use the change of energy over the course of your simulation as a direct diagnostic of like how much overall do I trust this, and if I'm interested in statistics that I'm not computing exactly with my scheme, then I don't have a good way to test those, right? Their accuracy, but I might be able to infer it from how well I'm satisfying these constraints, even though I'm not imposing them exactly. So I don't know, there's kind of two sides to that coin. Definitely for like long time simulations, this can get you into trouble, right? Because even if I have a little bit of div B, if I'm not actually resolving things to machine precision, and I have a little bit of growth of div B, then over a very long simulation, that could add up to be a big problem. So it depends on the case. Okay, so spectral methods in curvilinear domains. This should be pretty quick. So curvilinear domains are interesting from a spectral method perspective, and this is because the behavior, the analytic behavior of vectors and tensor components are different than scalars in curvilinear coordinates. So if I have a coordinate system where I have a coordinate singularity, then the analytic behavior of vectors and tensors is different at that coordinate singularity than scalars. So for instance, this is a plot of a smooth vector field. So, well, a smooth function of a vector field. So f is a function of x. And here I'm plotting the contour lines of this function f and the gradient in the arrows here. So this is a completely smooth, very well-behaved function. But if I look at the components of its gradient in polar coordinates, those coordinates, or those components are actually singular at the origin. So if I want to solve a spectral method, or if I want to solve a flow using a spectral method in like a sphere, for instance, to look at stellar convection, stellar interiors, or a disk using a global disk geometry, then I need to be careful, right? Because I don't want to use the same basis functions to represent scalars as to represent vector components, right? If I did that, I would lose the spectral property of exponential convergence because the analytic behavior of the function I'm trying to model, right, either the vector component or a scalar, is very different in those two cases. So you need to be a little more careful. You basically need to use basis functions that are adapted to these coordinate singularities and then behave differently based on whether or not you're a tensor component or a scalar. So this is true in the disk. This also happens in the sphere. So this happens at the poles in the sphere, and it also happens at the origin in the sphere. So I'll just briefly mention the way that you take care of this in the sphere is with a set of basis functions called the spin-weighted spherical harmonics. So the standard spherical harmonics are well behaved at the poles. So these give us a basis function that's really good for representing scalar values on the sphere. But if I want to represent vectors or tensor components, again, those are singular at the poles. And these spin-weighted spherical harmonics are sort of an extension of the standard spherical harmonics that take that regularity into account. So if I have a general tensor field T, so this is a general order tensor, sigma here is like a multi-index made up of plus or minus ones, where these indices are a recombination of the standard theta and phi indices. I can represent an arbitrary tensor as a sum over L and M, so again, the standard spherical harmonic quantum numbers, and a sum over all of the multi-indices of just numbers here. These are my coefficients, and then these are my spin-weighted spherical harmonics. And these bases have the nice property that if you take the gradient of one of these tensors, it ends up being just some number. So k here is some number times a different tensor. So this equation here looks a lot like the earlier equation, right, where I said the derivative of a Chebyshev polynomial was sparse in this other type of polynomial. Well, you have the same thing here. So you have for instance, the gradient of a scalar is a vector field, so that is sparse in the basis functions that represent vector fields, not the same basis functions that represent scalar fields. Yeah.
Are these different to like regular vector spherical harmonics or tensor spherical harmonics?
Yeah, so you can show these are a recombination of vector spherical harmonics. They're closely related. They're doing the same thing. But these give you a really nice way to generalize that to arbitrary order tensors. So the sigma can be an arbitrary order multi-index. I can have a fourth rank tensor and do the same decomposition, and all these properties hold. So at the end, this looks a lot almost like Fourier series, right? Where if I use the right trial and test functions, I can do general tensor calculus in spherical coordinates with banded operators. That's what the point here is at the end. Of course, writing your PDE in spin-weighted spherical decompositions is not fun for anyone. So what we've been working a lot on is making just a vector interface. So you actually don't type any components of your equations. You type in your equations sort of in vector valued form. So that would look something like this. I set up a field, or I set up a domain with a sphere, not important about the details. I say pressure is a scalar field, U is a vector field. And then I can actually write things like div U is equal to 0. Navier-Stokes equation sort of in vector form now, right? Laplacian U, grad P, U dot grad U. And I don't have to basically be aware of any of this decomposition. That's all done under the hood by the parser, and you can just enter your vectorial equations. And now this problem is also portable to different geometries, right? If I want to solve an equation in a plane parallel geometry with complex physics, I can write it all in. I can write MHD down. But then if I want to switch it to a sphere, I don't have to actually change the equation formulation at all. I just change the spectral domain up top. Okay, so just to finish a few videos of simulations in spheres. So this is a simulation of incompressible hydrodynamics with high-order Laplacian, so a single Laplacian, a bi-Laplacian, and a tri-Laplacian on the surface of a sphere. So this is a model that came out of biophysics. It's a model for representing like active biological matter. So basically, if you have a fluid full of bacteria, these bacteria, even though they're at low Reynolds number, they swim together and form patches that sort of behave turbulently and make these vortices. So this is a model equation for that, and the real point is that if you look at the pole of the sphere here, there's nothing funny going on, right? We're not excising any region of the pole. Nothing bad happens if a flow goes straight over the pole, right? That coordinate singularity really doesn't affect the solution at all, and that's just because everything that's going on there is taken into account in the basis functions. Here's a similar kind of fun example that illustrates this in the full sphere. So what's being plotted here is a cross-section of the full sphere. And inside of the sphere, we've used basically forcing terms to sort of mimic a cube that's convecting from the bottom up. So this is like a hot plate on the bottom, cold plate on the top. Gravity is just pointing down, not radial, right? We're not in a star. This is just solving convection in a box, but in spherical coordinates. And the point is that most test problems that you come up with for simulating stars don't actually do things like send fast flows through the origin of the star. So instead, this is sort of like an artificial way of doing that and actually testing that these basis functions are well behaved, even if you have high velocity plumes going straight through the origin of your spherical coordinate system. And there's no problems here. There's no time step restrictions associated with a small grid at the origin or anything like that. The basis functions just like do a good job since they analytically capture all of the coordinate behavior. They take all that kind of stuff into account. And then just sort of a fun example showing off some of the equation flexibility. So this is a simulation using what's called a phase field method to model a multi-phase flow. So here it's a transition between a liquid and a solid. So what I'm going to show you is this is an equatorial cross-section of a sphere, and the sphere is all water, and it's frozen outside of this black line and liquid inside of the black line. And we're going to internally heat the center to drive radial convection. So this is a toy problem, but the physics here is something like a model of the oceans in Enceladus or something like that, where you have an ice layer overlying a convective ocean. And yeah, what the interesting things here are, so the convection or the heating is sort of driving this radial convection, and that convection is melting the ice as it moves outwards. And some of the interesting science applications are looking at things like asymmetries in the ice shell in Enceladus. It's observed to be very like north-south asymmetric. And we're interested in questions like whether or not that's due to feedback with the convection. And so most people, they simulate these systems just in fixed spherical shells, but to actually include this like feedback of the geometry and the melting, you have to use these types of methods. And again, it's just a PDE. I mean, it has like these scalar fields that represent, volume fraction of ice versus water. They have forcing functions in them that basically give you the melting terms, the Stefan condition. At the melting interface, it's just another system of PDEs, but you type it in and it works pretty well. Yeah, so in this case, this is just a toy problem. So here we just did a fixed spatial heating profile. So just, yeah, heating is a function of radius. It's just some heating that's confined to the center of the sphere, but you could make that a nonlinear function if you wanted to do nuclear burning or something like that. You have to be a little careful because those terms tend to be extremely stiff, right? And if you're integrating them explicitly, you need to be a little careful. But yeah, in general, the heating term could be nonlinear if you wanted it to. Okay, that's the last example I had to show. So that's it. Yeah, thanks for listening. And if you have any questions, I'm happy to answer. Good. All right. Soccer time? Yeah. All right. Cool. Well, I guess that's it for today then, right? Because Rich is not coming back. So, okay. So see everybody Monday.